Hello, calculus students. This is Mr. Beck. Today we're going to be talking about the fundamental theorem of calculus. So the most important theorem of calculus is going to be our greatest discussion today, and I'm looking forward to it because we've been building everything up until this point. Just a quick recap of where we've been so far, especially in this chapter. In this chapter, we've been talking about first the antiderivative. So if we can take the derivative of something, we can go backwards, and that's called the antiderivative. And then we talked about the definite integral, which is the area underneath the curve, and what that area underneath the curve represents is a form of displacement. Whatever the rate function is that we're working with, we're displacing that rate function. So how much has been displaced, or what's the value of what that rate function has covered. And then what we did was we took approximations of those definite integrals, and because sometimes we don't have geometrical approaches to it, so we took a rectangle approach to it, which we called Riemann sums, and then we made infinite Riemann sums. And then those infinite Riemann sums allowed us to find the exact values. Now, with those infinite Riemann sums, we did them with polynomials, but sometimes that's not going to work, because what happens if we don't have summation formulas for, like, say, the sine function? So we have to have another approach to being able to find our definite integral. And that approach is what we're going to start with today. So where we are going to start is with the idea of what we talked about in 3.7 when we talked about differentials. When we went to approximate a function value, what we did was we took a known function value, figured out what the rate of change of that known function value was, and then we multiplied by the amount of change. So we took our known, we took the rate of change there, and we multiplied it by the amount of change. Now, with that idea in mind, we can approach that with, okay, what happens if we want to know where we are? So kind of like that, now we want to know what the function value is. To figure out where we are, we take where we start, or a known position where we start, and then we say, okay, what is the overall displacement? Because that's what our definite integral gives us. So what is our overall displacement to get to the next point? So this is, again, our known point plus the change, and then that gives us the unknown. This is known as the net change theorem. Net change theorem is pretty much what I just described right there for you. But if we do some quick algebra, if we subtract f of a from both sides, what we end up with is something called the fundamental theorem of calculus. So what does this mean? That if I have some function, and I want to know the definite integral of that function, what I could do is I can anti-differentiate the function and plug in the upper limit, subtract that antiderivative, plugging in the lower limit. And thus we have a much easier approach to finding the definite integral without having to go through the Riemann sums. Now, I enjoyed it, and I hope you enjoyed it, but I know not everybody does. So, anyway, we do have some guidelines for finding for using the first fundamental theorem of calculus. Typically, when we take our function, this is where I'm going to usually refer to this as f prime. I know this notation uses a little f and capital F, where capital F is the antiderivative. It makes a little bit more sense to write it in this format. So by writing in this format, what we're looking at is, we're looking at if we take the antiderivative of f prime of x, we are going to get f of x. And now this notation, we like to use a vertical bar, and sometimes you might even see it written as x equals b and x equals a. So what we're going to say is the definite integral from a to b of f prime of x dx will equal the antiderivative from a to b, meaning we plug in f of b and then subtract f of a. So working with this function specifically right here, the antiderivative of x cubed, let's go ahead, the definite integral of x cubed. We can say, let's take the antiderivative, and we are still going from the x value of 1 to the x value of 3. So plug in our 3, subtract, plug in our 1, and we get our overall solution, in this case of 20. A lot of students ask, well, when we had indefinite integrals, didn't we have to add the c? Why don't we have to include the c when it comes to definite integrals? Which actually is a really, really good question. The reason why we don't have to include the c has to do with the idea that if we take the antiderivative, and we can see it right here, if we take the antiderivative and we include that plus c, what will happen is we'll take c minus that same c, which cancels itself out. So it's a great idea to want to keep it in mind, but it's not really necessary because those constants are going to cancel each other out. So let's go ahead and apply. Now, when I originally did this problem, if you notice, I have some changed values. When I initially did this problem, one of the big ideas that I wanted to have is the integral of 2 over x is 2 natural log of the absolute value of x. But that's why I originally had this as -1, but this is a non-integrable region. And if you don't know what that is, that's totally okay. So if this is non-integrable region, then we can't really do the antiderivative. So um, we'll talk about that at some point, really, when we get into series and discussing series and proper integrals. Anyway, moving back to this problem. So the antiderivative of x cubed is 1/4 x to the fourth. The antiderivative of -9x squared is -3x cubed. And as I mentioned, the antiderivative of 2 over x is 2 natural log f to the value of x. Now you'll see that I do put brackets on here, and I like to put brackets instead of just that vertical line because the brackets kind of contain what I'm integrating or what I've taken the antiderivative of, so I know what to plug in. And if you notice, I put x equals 1, x equals 3. It's not required because this differential that we're using, this dx, means this should be an x and this should be an x. So all of those differentials work together in the antiderivative. Anyway, plug in our value. If we plug in our value, we will get to this point. Now, this is a great non-calculator answer. If we have a calculator answer, we'll get to that. And we can check ourselves. And this is going to be a first opportunity that I'm going to look at the graphing calculator here and say, hey, do we remember how to use the graphing calculator to evaluate indefinite integrals? So our shortcut key is Shift plus. So if we do Shift plus, I guess we have to go to the, there we go. All right, Shift plus, and it comes up with the definite integral. So we're going to take the definite integral from 1 to 3. And our definite integral, we have x to the third minus 9x squared. And then plus 2 over x. And then dx. So it'll come up with just what we said. Now, a lot of times that we want to know what the approximate or the decimal approximation is. Now, we do have this key down here that we use that we could say, hey, what's the approximate value of that? I really don't like to use it because every once in a while, the calculator will then do like another operation again with it. So the shortcut that I have students do if they want a decimal value is somewhere near like an integer. Go ahead, put a decimal point, and it'll come up with a decimal approximation for you. What that means is this should be an 8028 or an 803. Moving right along, problem number 2. What you see that I did here with problem number 2, I'd like to do a rewrite first to make it so that it's in its nicer form to work with. Take the antiderivative. Hopefully you're okay coming up with the antiderivative. Going from -8 to -1, which means we plug in -1. And this is a positive one because of the even exponent. And then we plug in -8, same thing, and then simplify. And again, this is a great non-calculator answer. With a calculator answer, this specific calculator will give us 4569 over 80 with a decimal approximation of 57.1125. Moving along. Now we get to example number 3. In example number 3, suddenly you see that we have the absolute value. And when it comes to the absolute value, suddenly we're like, wait a second, we don't really know how to evaluate an antiderivative with an absolute value. We haven't done this before. So what do? And our approach is we need to see, okay, can we break this up into a piecewise function? Because we do know that we can turn absolute values into piecewise functions. Well, how do we know the pieces? This part of the graph is above the x-axis. This part of the graph is below the x-axis. So we have to break it up into 3 regions. With our 3 regions, we have the first region from 0 to 1. And hey, how did we find our zeros? I guess I didn't really mention that. We found our zeros by factoring. So our 2 x-intercepts are 3 and 1. So now when we're finding our area, we're going to say, okay, the first region is the integral from 0 to 1. The second region is going to be the this part below the x-axis, which if you notice, that's why I am subtracting this. So I'm subtracting this because we are going below the x-axis. Then adding the third part. And then you can see that I've gone through the work, which each region ends up being 4/3. So we have 4/3 plus 4/3 plus 4/3 for a grand total of 4. Great opportunity for us to take a look at our graphing calculator. With our graphing calculator, what we're going to have is, well, where is our absolute value? So once again, I'm going to do Shift plus. Shift plus, we're integrating from 0 to 4. And that will get there. Now our absolute value is located on my favorite button, this menu. So the absolute value of x squared minus 4x plus 3, x squared minus 4x plus 3 dx. And you'll see we do get the answer of 4. So yay, very, very excited. So moving right along again. To this problem. To find the area of the region bounded by the graphs of the equations y equals negative x squared plus 4x. And if you can tell, one of the things that I did with this problem was I said, okay, well, if I want bounded by the graphs, I need to know what this graph looks like. So I made a very, very quick sketch. So the quick sketch that I did allowed me to say my x-intercept is 0, my x-intercept is 4, and I know that this is a negative parabola. So seeing as how this is a negative parabola, then I am going to go ahead and set up my integral. I'm integrating from 0 to 4 because I want it bounded by the x-axis as well. And then our function dx. And I derivative from 0 to 4, and I get 32 thirds. Okay. So what is it that I wanted to show with this on the calculator? And today is going to be a great opportunity for us to really look and say, how can we use the calculator to our benefit to help us come up with our answers? So without further ado, let's go ahead and go to the graphing screen. I'm going to graph negative x squared less 4x. And I have a graph that looks like this. So one of the features that I want to explore is under menu, analyze graph. I want to look for the bounded area. So apparently I am in complex numbers, so it's warning me, so change to real or complex. So I need to change my settings really quickly. I don't think it's there. Maybe it's document settings. So yeah, real or complex. Let's go ahead and make this real just so that we can do it properly. All right, so we're going to bound between the function and the x-axis. And what's nice is it automatically comes up with your intersection points. And if you notice, it says 10.7. Now, if you look over here, the exact value I have is 32 thirds, not 10.7. So how do we reconcile that? If you hover over this, and I'll see if it works on my computer. If you hit the plus button, it'll expand your decimals. If you hit the minus button, it'll contract the decimals, but we want to go to at least 3 decimal places. And so by going to at least 3 decimal places, we can see that it's 10.6666 repeating, so on. Another approach of what we could do, and just something else you should know, if you hover over this and you hold down, eventually you'll be able to clamp it shut and you can move this so that it's not overlapping with all of our different functions and so forth. Anyway, the other approach of what we could do with this problem is, if you notice under the menu, analyze graph, we do have the integral. So lower bound, we could say, and honestly, I like to type it in rather, so it's not just an approximation. Lower bound is 0, my upper bound is 4. And then once again, you see it says 10.7, which hover over it, plus, 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 we get all of our decimal values. And we're excited about that. So let's go ahead and move on to the next ideas. So the next ideas that we have here is something called the mean value theorem for integrals. And when it comes to the mean value theorem for integrals, what I'd like to start with is more of, well, what was the mean value theorem for derivatives? The mean value theorem for derivatives said, if I have, let's see, let me write this out so that you can see it. The mean value theorem for derivatives said, if I have an average rate of change on a function that's continuous and differentiable in the interval, at some point I'm going to have the instantaneous slope that's the same as the average slope. So what I'm looking at is average slope is the same thing as the instantaneous slope. Okay, well, how does that apply for integrals? And I set up this idea a little bit better last time when I was talking about Let's talk about lower Riemann sums and upper Riemann sums. If I came up with a approximation for area of the entire region where I know it's like the lowest value, I know that's an under approximation. This one we can see is an over approximation. So kind of like with the intermediate value theorem, we say, okay, area is a differentiable function. And since area, or a continuous function, I should say, since area is a continuous function going from the lower area to the upper area, at some point, we have to have the average area that's going to exist represented by this rectangle. So the reason why this is called the mean value is because at some point, at some c value, which is going to be this c value, at some c value, the average area is going to equal the instantaneous, meaning the definite integral. So hopefully that makes a little bit of sense for you. So we could see this as, okay, well, how does this mechanically work? We have our definite integral, the integral from a to b of f of x dx. Obviously, that's that pink region that I was shading. And it's going to be the area of the rectangle. So the area of the rectangle, the horizontal distance is b minus a. The vertical distance is f of c. And that f of c has a special name called the average value. We'll talk about that in a moment. So f of c times b minus a equals the definite integral. Again, what does that mean? It means that we can come up with some rectangle that the average rectangle is going to equal the instantaneous value of that definite integral. So let's apply it. I want to find the value c guaranteed by the mean value theorem in this situation. So I drew the graph of cosine. We can see that right here. And going from negative pi over 3 to pi over 3. So let me approximate. Let's just say that's going to be right here and right here. I know that's not definitively the case, but let's just approximate with that. So f of c times b minus a equals my definite integral. I evaluated my definite integral, and that's what this is, which this ends up reducing to the square root of 3. Don't forget your trig, by the way, the sine of pi over 3, sine of negative pi over 3. And then I also, if you notice on this step, I multiplied by the reciprocal. So this right here, this 3 squared to 3 over 2 pi, this 3 squared to 3 over 2 pi is known as the average value. So once again, you could see that f of c is my b minus, or f of c is that average value. And then I went ahead and solved for c. I said, okay, if my function is cosine of x, where does cosine of x equal that? And don't forget, based off of the interval, the calculator only comes up with a positive answer, but don't forget that that negative answer is still a possibility as well. Same thing over here. So when it came to this problem, first thing I did look for is this function continuous over the interval that I'm working on? And the answer to that is, yes, it is. So then I found my definite integral. It equals f of c times b minus a. Simplified, and eventually I will get this 2, which once again, the average value is 2 over that interval. Since that average value is 2, set my function equal to 2 and solve. Where I do have 2 potential cases for this problem, that's not exactly what's happening. It's not 2 potential cases, it is only 1 case, and that's because it only occurs 1 time on the interval from A to B, excuse me. Now this average value, the average value is kind of like the more important concept of what we're working with as far as what the AP ends up assessing. So the AP is assessing what's the average value. And it has more meaning because typically, and I'm going to use this drawing as a representation. So this function is a rate function, and we want to measure what that rate function is. One of the things that I did in class, and I had a problem that described me walking on a treadmill, and I used Riemann sums to say, okay, well, I had this distance, I had this distance, I had this distance, this distance, this distance, et cetera. And then my last question on that was, what was my average speed over the entire region? So in essence, I was looking for the average value at that point. What we did was we summed up everything and divided it by my time frame, divided by my time. Well, the summation is what the definite integral gives us, and we saw that with our infinite Riemann sums, and then we divide by the interval that we're working on. So, very, very natural approach to how we look at this. And so we could write it that way, as I see right here. And what I do like about this is if I show this as what's the antiderivative, f of b minus f of a over b minus a, really it looks like the average rate of change of the antiderivative. Now the antiderivative tends to be known as the accumulation function. The reason why it's the accumulation function is because the antiderivative gives us whatever that accumulation is. So with that accumulation, we just basically say what's the change in accumulation divided by the change in time. So we could turn this into an average rate of change, which goes back to why it comes from the mean value theorem for derivatives. So we could say at some point the average rate of change equals the instantaneous rate of change. So in this case, the average accumulation is going to equal the instantaneous accumulation. Moving right along, just go ahead and find it. I have a problem where I have a cost function, and with that cost function, I want to know what the average cost of production is. The average cost of production is going to be the integral from 0 to 8, because that's the interval that I'm working on, of my cost function divided by my interval using the calculator. Let's go ahead and show this just because I hate to just like throw numbers at you, and it's a good practice. So once again, shift plus, actually I forgot that it doesn't work on the keyboard, so shift plus definite integral 0 to 8. And this is the first time that I think I've shown you guys using a variable other than x, and really with a variable other than x, it works the exact same way. Let's go ahead and say q to the third. Q to the third, I lost my function, okay, minus 12q squared plus 60q. And then now our variable of, or our differential is dq. So hit enter, 896, and then we divide that by 8, and that's how we get the 12. So the average cost of production is $112. Really, it's supposed to be more of $112,000 per 1,000 units. So if I ask for a unit cost, I can give it to you as a unit cost. More specifically, $112,000 per 1,000 units. So this is probably a situation where you're producing thousands of units at a time, as opposed to just one unit. So continuing along. Second fundamental theorem of calculus. So the first fundamental theorem of calculus said, the integral from a to b of f of x dx was f of b, capital F of b minus capital F of a. Second fundamental theorem of calculus really shows a relationship between derivatives and integrals. It says if we are integrating from a known value to an unknown value of some rate function, and if I want to know the rate of change of that accumulation, I simply just have to plug in x to that function. So that's what I showed here. So the short form is if I want to know what f prime of 1 or f prime of x is, so if I want to know what f prime of x is, I simply just have to plug in an x in place of the 1, or sorry, in place of the t. Now, kind of going through a long format here, that this is a function that I can find the antiderivative for. When I find the antiderivative for, plug in x. What I didn't show was 4/5 0 to the 5/4, which is of course 0. And then if I want to take the derivative of it, the derivative of it is once again x to the 1/4 power. So that's the long approach. Now, what is f prime of 1? I went ahead and found f prime of x right here. F prime 1, just plugging in 1 is still 1. What does it represent? And so I also found f of 1 to give a little bit more context to this problem. So f of 1 was 4/5. So at the moment when we've accumulated 4/5 of whatever these units are, we know that the rate of change is 1 unit per second. So it kind of like by finding both the antiderivative and the function itself, it kind of gives more context to what's going on. And same thing if I plug in 16. When I plugged in 16, then you could see that when I've accumulated 128/5 units, I can say its average rate of change, or sorry, its rate of change is 2 units per second. So it shows a good representation. But anyway, how do we find it? Well, here's a situation where we are not We are not integrating from a known value to an unknown value. We're integrating from a known value to a function. This is what's going to occur more often than not. We don't just say from a known to an unknown, we say from a known to a functional value. Well, let's look at this and say, okay, the more expanded idea behind the second fundamental theorem of calculus is if I integrate from a changing function to another changing function, but then I want to know the rate of change of that situation, which I know is really, really complicated. What I do, and this is to really cut to the heart of it, plug in the upper function, multiply by its chain. And the reason why we're multiplying by the chain is because once we take the derivative, the chain rule is going to apply. So then plug in the lower function and multiply by its chain. And that's what I did right here. So I plugged in my upper function, and I'm using the second fundamental theorem, so there's no need for us to find the antiderivative of this. If you really wanted to, it's going to be kind of interesting. So if I do shift plus, you can hit delete and it goes to the definite integral. So if I wanted to find the antiderivative of the square root of 3t squared plus 1 dt, boom, very, very complicated function. And how's a student supposed to know that? Well, students are only supposed to know that once we do trig substitution to actually help with this. So we will do this with a trig substitution. So with our trig substitution, actually, I'm not going to do that right now, trig substitution. And we don't need to know it because what's our goal? Our goal is to find f prime of x. So let's just take the derivative of the integral. So by taking the derivative of the integral, we're going to be allowed to say, just plug in the upper function, multiply by its chain, plug in the lower function, multiply by its chain. Now, obviously, this does equal 0. And since this does equal 0, there's really no need to write it. I like to write it just to kind of represent so that we understand. Plug in the upper, multiply by the chain, plug in the lower, multiply by the chain. Which we could see, do the same thing here. So rather than find the integral of cosecant, which we have not done yet, but we're going to be doing sometime very, very soon. So plug in the upper function, multiply by its chain, plug in the lower function, multiply by its chain, simplify. Same thing here, plug in the upper function, which I think I just cut to the chase. And so plug in x squared and square it, multiply by its chain, plug in 0, we get 0. Now, I've also, so that's the end of the fundamental theorem of calculus and really the second fundamental theorem of calculus at the exact same time. What we could do, or what I'm planning on doing is, I'm planning on going into a little bit of integration by substitution. When it comes to my integration by substitution, what I'm looking for is, it's an answer to how do I come up with the antiderivative of more complex functions. We can see on the calculator how this is like a really, really complicated antiderivative. Because that's a really complicated antiderivative, most people are like, how am I supposed to know that's what I'm doing? And the answer is, it's not easy to determine that right from the beginning. So let's look at it and say, can we come up with a strategy for how to approach a problem like this? So the strategy that I'm going to begin with is, I'm seeing a product here, this product, and then there's an exponent. So there's a lot of different things going on here that I'm going to have to compensate for. And if we take it step by step, we're going to be able to say, okay, how do we analyze this, and how do we appropriately analyze this, so that we can make it easier, and cut to the heart of what's really being integrated here. So if u equals x squared plus 1, then the differential of u is 2x times the differential of x. Okay, so if you notice, I'm taking the expression that I'm beginning with, and I'm going to break it apart into those two different components. So, and if I do my u-substitution, what we really see is this problem is really the integral of u to the 4th du, which is an easy antiderivative, and then a resubstitution. So what I've done is I've turned a more difficult looking integration into a simpler integration. Actually, the simpler integration didn't occur there, it occurred here. But this gets, as I said, gets to the heart of what is happening in this antiderivative. Okay? This antiderivative is really the x squared plus 1. The 2x is the chain rule. So it goes back to, okay, well, all the problems that we've done so far, have been a lot more of antiderivatives of, not these ones, antiderivatives of functions that we already knew. Or how about power rule? That's what I was trying to say. Antiderivatives of all my power rule problems. I also did antiderivatives of sine or cosine. So all of the simple ones that we have worked with in the past. And those are more power rule and then like trig derivatives. But what happens if we have a function that has a chain rule involved? So like f of the composition of functions. So when we found our derivative, it became f of g times g prime. Now we're really working backwards. And that's what the U-substitutions allow us to do. They allow us to work backwards so that we can say, hey, this really was a composition, and we can simplify our approach. So on this example too, if you notice, I've highlighted what's inside the composition of the function. So what's inside a bigger function. So u equals 1 minus x squared. Du, as you see, is negative 4x dx. Now rewriting the cube root of u times du. So again, take it back to a much simpler integration problem. So these problems are really the same. It just says what's the real focus of our problem. And then in the end, don't forget to take it back to x. Now, the moment you integrate, you must put the plus c at that moment. Example number 3, one more time. So what's our inner function, or really what's the main function that's being integrated? That main function is going to be tangent. The derivative of tangent of x plus 3 is secant squared, and we can see that that's there. Brought the 3 on the outside because it really wasn't essential for the derivative or antiderivative. So u du, which of course I wrote that way. Antiderivative, don't forget to add the plus c at that moment, and then resubstitute. Then we get to this problem. This problem, let me go ahead and erase. Unfortunately, my pen died right there, so I'll do a quick charge on it. So what you can see at this problem is I included a 4 here. Now, I hate to look at it at that point, or right at the beginning and say, okay, why is the 4 there? That's what I was trying to erase. So let's get rid of the 4. Okay, charge the pen one more time. All right, so if I say, okay, do I see a function within a function? A function within a function is 1 plus x to the 4th is being squared, so that's what I made as my u. And then my du is 4x cubed dx. And so at this point, I have 2 different approaches that I could take. One approach is I have x cubed dx, so let's solve this so it's du over 4. And so I could write this as du over 4. So that is one approach to the problem. The approach that I personally like to take is, hey, I need a 4x cubed dx. I'm missing a 4x cubed, so as long as I'm off by just a scalar, let's introduce the scalar at that moment, but then compensate by introducing its reciprocal. And that's how I like to approach the problem, just because it's a little bit more creative, more fun. It's less mechanical and more targeted. This is how I'm going to manipulate my situation to get what I want. So then integral of 1/4 u to the negative second du, and just go ahead and anti-differentiate, and then plug in, resubstitute. Example number 5. I love example number 5. If you could see, I have taken 3 distinct approaches to this problem. The 3 distinct approaches of the problem are going to be, are really designed to say, this problem does not necessarily have to be done one way. So if we take a look at this situation, the very first thing that I have is, I decided to say u equals sine of x. So of course, du is cosine of x. So we have 3 times u times du, which is what I have here. Integrate, I get that expression. All right, let's change colors. Well, what happens if I want u to be cosine of x? Well, if u is cosine of x, then I have 3 u, oops, u was the cosine, and then du is the sine dx. So let's focus on these 2. And if you notice, working through 3u du, get to the answer. If you notice, I have 2 very, very distinctly different looking functions. So these distinctly different looking functions, how are these the same? They're not really supposed to be the same value, right? Well, let's take a look at what the graph of these look like. So once I started having a messy amount of mess on my document, I hit Doc B. Doc B clears my scratch pad. So let's graph this. What is 3, pardon me for 1 second, hit tab. What does 3 halves, and I have to put sine of x in parentheses. So sine x squared. What does 3 halves sine squared look like? It looks like that function, which hopefully everybody expected that. So 3 halves sine of x looks like that. Then what does 3 halves, hit tab again, what does negative 3 halves? And then cosine of x, cosine of x squared. What does that look like? Well, as you can see, they are 2 distinctly different looking functions. So how are these the same? They're the same because that plus c. This is a great opportunity to say this plus c means that they're just off by a shift. So that shift, in this case, it looks like it's going to be down, I think it's down 3 halves. So how do we algebraically reconcile this? Well, if you guys remember that sine squared is equivalent to 1 minus cosine squared. So if we looked at this as 3 halves times 1 minus cosine squared x plus c, 3 halves minus 3 halves cosine squared x plus c, what ends up occurring is this 3 halves and this c would join together to be that c, if I wanted to algebraically reconcile this. Now, it's not necessary, but it is what it is. All right, the third approach is to take a double angle formula approach. And I like this one just as well. And there is an AP problem one year that had a situation like this to say which one of these is, or this, which one of the following is not an antiderivative. So it used the idea that double angle formulas are important. Officially, you don't need to use the double angle formula on the AP test, but the more you know, the more you're going to be able to do and do very, very quickly. So anyway, this answer, when we did this, we get the cosine of 2x, which if we, depending on which double angle formula for the cosine of 2x, if we use 1 minus 2 sine squared of x, you can see how we got the first situation. If we use 2 cosine squared x minus 1, we'd get the second situation. So that one's that, and that one was that. Anyway, last problem that I did with students is sine squared of 3x. And if you notice, I did do some manipulation there. What we want to focus on is what's being squared is what our u is. So what's inside the inside of another function. So what's inside of another function is the sine, derivative is 3 cosine 3x, and this is where I'm like, hey, I don't have a 3, so let's introduce 3, and multiply by the reciprocal at the same time. That way our function, or really our integration is 1/3 u squared du. We get 1/9 u cubed plus c, and resubstituting looks like that. So thank you for beginning the journey of integral calculus with us, and definite integral calculus, where we're coming up with our answers very quickly. Hope you enjoyed it, and I look forward to seeing you next time. Bye.